acids and bases there with this PowerPoint. Now you have the PowerPoint on Edmodo from 5th year. Common examples of household acids, okay, and they're your common examples of laboratory acids. Now the first scientist that started to put forward a theory on acids was Arrhenius. So he said that an acid was a substance that associates in water to produce or to form H+ ions, okay. Now this is an example here. So you have HCl donating a proton or H+ ion, forming H+ and Cl-. And then underneath you have your general equation of an acid, HA. Remember that acids have to have a proton. So if you're trying to identify something as an acid, it has to have a H. It has to have a H so that it can donate that H. Now, you need to be able to classify acids as monobasic, dibasic and tribasic. So in the first equation there, you can see the nitric acid, HNO3, is donating 1 proton per molecule. So nitric and HCl would be examples of monobasic acids. Sulfuric H2SO4 is a dibasic acid because it can donate 2 protons per molecule. And then our example of a tribasic acid is phosphoric acid because it can donate 3 there. And you can see it in the last equation, it donates 3 protons. Look at the number next to the H. That will tell you the classification of the acid. Now you need to be able to obviously define an acid as according to Arrhenius, but you have to be able to distinguish between strong and weak acids. So a strong acid is one that fully dissociates, and you can see your example there, and weak acids do not fully dissociate. When you have strong acids in the equation, you're going to see an arrow that goes to completion, and you won't have any mention of a Ka value in the question. At the bottom there, you can see the dissociation of ethanoic acid. Look at the arrow in the middle of the equation. It's a reversible reaction. It's a reversible arrow. And you would have a Ka value there now, which will tell you that the acid is weak. Common examples of bases, household examples of bases, and there are common laboratory bases, okay? Now, Arrhenius' theory of a base or definition of a base is a substance that associates, again, in water to produce OH- ions, okay? And you can see the 2 equations there. And then again, you have to be able to differentiate between a strong and a weak base. So a strong base is one that fully dissociates. A weak base then does not fully dissociate. Now, this looks a bit confusing and I left it in, but like you can see what's happening there. The top equation represents an acid dissociating to produce H+ and A-. The second equation is representing the base. You have XOH making X+ and OH-. And you can see there then when you're reacting an acid and a base, you're going to make water. So the H+ and the OH- combines to form the water. And then the A- and the X+, they're oppositely charged ions. They'll attract to form your salt, which is called AX there. Now, the other thing you need to know is some shortcomings or some sort of problems, limitations with Arrhenius' theory. So the first thing that you need to say is that Arrhenius said that for acid-base reactions, they have to happen in water. So he kind of over-relied, I suppose, on the dependence of water. So like that would have eliminated any acid-base reactions that happen in other solvents like benzene or ammonia, for instance. So look at number 2 there. Not all acid-base reactions happen in solution. So for example, if you have ammonia gas and hydrogen chloride gas, when they combine, you do form a salt, ammonium chloride, but there is no water involved there, okay? According to Arrhenius, he said that salts should be neutral, and that's not always the case. Now, that number 3 isn't a great one, but this is a very good limitation. Look, Arrhenius thought that acids associated to produce H+ ions, but protons are H+ ions. They're the same thing. Protons and H+ ions can't exist on their own. So when an acid actually dissociates, then the proton goes to the H2O there. So hydronium ion is formed. That's another limitation with Arrhenius' theory. So if you just say, if they ask you for limitations of Arrhenius' theory, you're going to say that he relied on the dependence of water, that not, other acid-base reactions happen in other solvents like benzene and so for methylbenzene, things like that. He also said that protons occur on their own or can exist on their own, and that's not the case either. They form these hydronium ions. That's another limitation of Arrhenius' theory. Bronsted and Lowry then came along and put forward definitions of acids, a substance that associates, a substance that donates protons. An acid is a proton donor and a base is a proton acceptor. Now you must be able to identify acids and bases according to Bronsted and Lowry. So you can see here on the left hand side, you must spot the difference between the left and the right. So the HCl is losing or donating a proton and it's becoming Cl-. The H2O there is acting as a base, because from the left to the right, you can see that it has accepted a proton, okay? And you can see there's, again, nitric acid there in water, so you need to be able to identify which is acting as the acid. How will you know? Well, which of the 2 on the left is losing a proton? And you can see it's the HNO3 is losing a proton, becoming NO3 minus. The water is accepting a proton, becoming H3O plus. So the water there is acting as the base. In the second two equations at the bottom there, look, you can see that's the two equations to show the two protons that are dissociated or that are donated by sulfuric acid, because sulfuric acid, remember, is a dibasic acid. So in the first equation there, you can see one proton is being donated by the H2SO4 going to the water. And in the second equation, the second proton is being donated and you're forming your SO4 minus 2. Okay. Bronsted and Lowry then said bases were proton acceptors. You can see an equation there where you have the NH3 accepting the proton, becoming NH4 plus. Here the water is actually acting as an acid because it's donating a proton. So you can see that water can act as an acid and a base. So we call something like that amphoteric. Aluminium oxide is another substance that can act as both acid and base. So can you identify here now which is acting as the acid, which is acting as the base? Okay. Now neutralization, this I'm going to fly through this because you did this in junior cert. It's a reaction between an acid and a base to form salt and water. Your definition of a salt, and then the examples, everyday examples of neutralization. You have some there in the PowerPoint. Now, lastly then, conjugate acid-base pairs. Now your definition of a conjugate acid-base pair is consisting of an acid and a base. So it's a pair, two things that consist of an acid and a base, and they differ by a proton. So when an acid loses or donates a proton, it becomes a conjugate base. So you can see in the example at the bottom there, you've got your ethanoic acid there, CH3COH. That's donating a proton, so it's acting as an acid. But once it has donated the proton, it becomes the CH3CO minus is a conjugate base because that's capable of accepting the proton and going back to the acid again. So once the acid donates the proton, it becomes a conjugate base. When a base accepts a proton, it becomes a conjugate acid. So you can see the example there of the base NH3 is accepting a proton. So the the NH4 plus then is your conjugate acid. And there are some examples there. But I'm going to do one out there now on the show me board, okay? So here you can see you're asked here now to identify what species is acting as a base, what's acting as an acid. Now this one is straightforward because there is no proton here. If there is no proton in a species, it cannot act as an acid because Bronsted and Lowry said that acids donate protons. So this has to be the acid because it's the only one with a H. It donates the proton. Now you need to link it to the conjugate base and you'd write it out properly, conjugate base, okay? Is this behaving as a base? Yes, it is. It's accepting a proton, adding a proton, and you're making that then would be your conjugate acid, okay? Now, second now, and I'll just clear that. Now, the next thing I wanted to quickly do there now was to go through again how you would figure out what's the conjugate acid, what's the conjugate base. So if you're asked to write the conjugate acid of H3PO4. Now, you're looking for the conjugate acid, okay? If you're looking for the conjugate acid, then the H3PO4 must be behaving as a base. Bases, how do you form conjugate acids? When they accept a proton. What does a base do? It's a proton acceptor. So add a proton on to that. Actually, sorry now. I just need to clear that for a second. I took down the wrong thing. It's H2PO4 minus. That's what you were asked. Sorry, that was the question. That's an exam question. So going on there now, you're asked to find the conjugate acid of that. If you're asked to find the conjugate acid, it is acting as a base. Okay, if the H2PO4 minus acts as a base, then what does it do? It accepts a proton, so add a proton on to that. Now be careful with the charge. There's a -1 charge there at the moment, then you're adding a +1. So what's that? -1 plus 1, that's going to give you 0. So there's no charge there on that when you're looking for the conjugate acid, okay? So if you're looking for the conjugate acid, it's behaving as a base, accepting a proton, and that's what you get, okay? Now, same species again, H2PO4 minus, but this time you want the conjugate base. If you want the conjugate base, then it's acting as the acid if you're forming a conjugate base, right? So H2PO4 minus, acting as an acid, donate a proton this time. So take away one of these protons, so you'll end up with HPO4. Now, what about the charge? -1 currently, minus this time a +1. Always protons are +1. So you always have a +1 in the bracket. Minus and a plus gives you a minus. So you're ending up there with minus 2. Okay? Right. Thank you.